Sections 2.7 and A11, Complex Numbers and Complex Zeros of Quadratic Functions. So we need to talk about imaginary numbers. Well, the deal is that, first off, if you're dealing with real numbers and you square a real number, it's always non-negative. And I say specifically non-negative because if you square a negative number, it's positive. If you square 0, it's 0. And if you square a positive number, well, it's going to be a positive number. And that is, there's no real number such that x squared is equal to negative 1. But if we extend ourselves to a different field, and mathematical field is the term, then we get what's called the imaginary unit. And that is I squared is equal to negative 1. And if that's the case, then we're going to say that I is equal to the square root of negative 1. And if you recall, we can break up radicals using the product property for radicals. That is, the square root of a times b is the same thing as the square root of a times the square root of b. But be aware that anytime you have negatives on the inside, you must come up with i's first before you can multiply radicals. And so this property for radicals and products, this is only true if a and b are non-negative numbers. So now let's simplify the following in the complex number system. Let's do the easy part first. The square root of the negative gives me an I. And then I'm left with the square root of 175. Well, for 175, we can rewrite that as I times the square root of 7 times 25. Since 25 is a perfect square, that's then going to be 5i root 7. Now, just so that you know, multiplication with an I is commutative. That is, the order in which we multiply things doesn't matter. And so sometimes you may need to write it as 5 square roots of 7 times I. These two are really the same. It's just going to be preference, or if someone demands it to be written a certain way. Now if I've got the square root of negative 25 times the square root of negative 9, do not make the mistake and try to multiply them first. That's incorrect. Because these numbers are negative, we cannot multiply before we get the i's. And so the square root of negative 25 is really just going to be 5i. The square root of negative 9 is just going to be 3i. And so now we have 5 times 3, which is 15, and we have I times I, which is I squared. Well, remember that I squared is equal to negative 1. And so that is, this is going to be 15 times negative 1, or negative 15. If I have negative square root of negative 28, we've got two things to deal with. First, we've got negative I. The square root of the negative becomes I, and then I'm left with square root of 28 on the inside. Well, let's see if it'll reduce. Divide by 2, that's going to be 14. Divide by 2, that's going to be 7. That is negative 2i root 7. And once again, it would be perfectly fine to also write this as negative 2 root 7 times I. Just be careful not to accidentally slip the I under the radical. Now a complex number is a number of the form a plus bi, where a and b are real numbers. But realize that a could be 0, b could be 0, or any other real number you could come up with. And so the deal is that a is going to be our real part. Specifically, if b were 0, a is the only thing that exists, and that is real numbers are always complex numbers. Now the b is the imaginary part. And once again, if a is equal to 0 and b is not equal to 0, then bi is purely imaginary. And if a is not equal to 0 and b is equal to 0, then a is purely real. When adding or subtracting complex numbers, we're just going to treat complex numbers as binomials. And then you're going to treat I the same way you would x. That is, if you have 2i plus 2i, those are like terms, and you would really get 4i. So now let's write each expression in standard form a plus bi. If I have 3 plus 4i plus 1 plus 2i, well, that's just going to be drop the parentheses because of the addition. 3 plus 4i plus 1 minus 2i. Then combine like terms. 3 plus 1 is 4. 4i minus 2i is plus 2i. And we're finished. This is in the form a plus bi, and sometimes you will have to write it as a plus bi for it to be correct, so just watch out for the requirements on my labs. If I've got 3i minus 2 minus 5i, step 1 we need to distribute that negative. That's going to be 3i minus 2 plus 5i, which then we just combine like terms. 3 plus 5i is 8i, and then minus 2 is minus 2, and since 8 was positive, there we are. Negative 2 plus 8i. This is in the form a plus bi, and we're done. When we multiply complex numbers, we're going to treat them as binomials, and then of course we're just going to deal with I as if it's x. That's all. And so things that we need to remember is that when we're dealing with I, powers of I simplify. That is, I to the first is I to the second is negative 1. I cubed is really I squared times I to the first, or negative 1 times I, so it's negative I. I to the fourth is really I squared times I squared, which is negative 1 times negative 1, so that's positive 1. So in general, when we're dealing with powers on I, these things will always repeat in iterations of 4. So now if I want to simplify I to the 37th, I'm going to use a trick. And that trick is I'm going to divide the power by 4. And I'm going to show you what that really means mathematically, but let's first just do this division. 37 divided by 4. 4 goes into 37 9 times. 9 times 4 is 36. 37 minus 36 is 1. Now why in the world did I do all this? Well, the reason I did all this is because really what this tells me is that I can rewrite I to the 37th using power rules. Specifically, this is the same thing as I raised to the 4th power 9 times I to the 1st. So notice that my divisor is I to the 4th. The 9 is the number of times I to the 4th is raised to the power of that. But this is really 1 to the 9th. So that's 1 to the 9th times I to the 1st, or just I, which means that my final answer is I. Let's try it again with I to the 20th. Once again, the shortcut is really that you're just doing division and you consider the remainder. So let's say, what is 20 divided by 4? Well, 20 divided by 4 is 5. 4 times 5 is 20. Subtract, we have our 0 remainder. Well, that really means that I to the 20th could be rewritten as I to the 4th raised to the 5th power. I'm just using power rules here. But I to the 4th is 1, so this is 1 to the 5th, so that means I to the 20th is really 1. Once again, we're just looking at the remainder, where the remainder of 0 is equivalent to I to the power of 4. If our remainder is 1, it's the same as I to the 1st. If our remainder is 2, it's the same as I to the 2nd. And if the remainder is 3, it's the same as I cubed. Now let's try it again. If I have 7i times 9 minus 4i, step 1, just distribute. 7 times 9 is 63i. Then 7i times negative 4i is negative 28i squared. Remember, we just treat the i's like variables. Then we need to simplify those I powers. So I squared is going to be negative 1, and so this is then 63i minus 28 times negative 1, which is then going to leave us with positive 28, but to put it in standard form, this needs to be 28 plus 63i. More multiplications. If I have 3 minus 4i times 7 minus 2i, and just treat it as binomial multiplication. That is, use the double distributive property, or if you would rather call that FOIL in this case, that's fine. 3 times 7 is 21. 3 times negative 2i is negative 6i. Negative 4i times 7 is negative 28i. And then negative 4i times negative 2i is positive 8i squared. Then we should combine like terms and simplify powers on I as much as possible. This then gives me 21. Minus 6 minus 28, those are like terms because of the i's. That's going to give me minus 34i. Then 8 times I squared is really 8 times negative 1, so that is minus 8, because negative 1 times 8 is negative 8. 21 minus 8 is going to leave us with 13, and then negative 34i is just negative 34i. No more like terms to combine. We're done. 11 minus I quantity squared. Do not square the terms. This is a binomial squared. It's the same as 11 minus I times 11 minus I. If you would prefer to use the perfect square trinomial formula, that's perfectly fine, because this becomes a perfect square trinomial as it's a perfect square. But you could just FOIL it easily. 11 times 11 is 121 minus 11i plus I squared. That's going to give us 121. Then that's going to give us 121 minus 11 is minus 22, because they are like terms because of the I. Plus I squared is really minus 1. Then 121 minus 1 is 120 minus 22i. There we are. 3 minus 8i times 3 plus 8i. Notice that this is a product that is the difference of squares. And so if you already know how this jumps because of the difference of squares formula, that's fine. But if you've forgotten, you can just double distribute or FOIL. 3 times 3 is 9. Outer is plus 24i minus 24i minus 64i squared. But then what do we get? This is now going to give us plus 24i minus 24i, that's 0. So we get 9 minus 64 times I squared is really plus 4. 9 plus 64 is 70. So if we want to talk about division of complex numbers, first we have to talk about the complex conjugate. And the reason we need to talk about the complex conjugate is because division of complex numbers isn't going to work in the same way we did long division with real numbers earlier. This process is going to be slightly different. So now let's talk about the complex conjugate. That is, a conjugate is a binomial formed by negating the second term in the binomial. That is, when you have a binomial, just change the sign of the middle term and you get the conjugate. And so if I've got 3 plus 2x, all I need to do to find the conjugate is change the plus to a minus. That's all. The complex conjugate of a plus bi is a minus bi. They're called complex conjugates. Well, what's interesting here is if you recognize this, this is really, if you multiply them together, the difference of squares. And so notice that if you have a plus bi times a minus bi, we're going to get a squared minus abi plus abi minus b squared I squared. Those terms cancel out, and so we're always going to get a squared plus b squared because I squared becomes negative 1. And so what happens is when you multiply a complex number by its complex conjugate, you will always get a real number. So then, if we're going to divide two complex numbers, what we're really doing is we're multiplying by one in disguise. Specifically, that one in disguise is going to be the conjugate of the denominator over the conjugate of the denominator. And if you are recognizing that this is the exact same thing that we would do with binomials of radicals, then great, because remember that a complex number is just a radical with a negative in it, and so that's what we're dealing with. Then we'll simplify as much as possible, dividing by the resulting real number. So if we have 5 minus 3i divided by 3 plus 4i, we need to get this in standard form a plus bi. Well, the first thing we need to do is find the complex conjugate of the denominator. That's just going to be 3 minus 4i divided by 3 minus 4i. Then we multiply tops and bottoms. 5 times 3 is 15, minus 20i, minus 9i, plus 12i squared, divided by. And if you want to jump straight to, this is going to be 3 squared plus 4 squared. That's fine, but just to confirm everything, 3 times 3 is 9, minus 12i plus 12i minus 16i squared. Then we can simplify this more. Notice negative 12i plus 12i is 0, and then I squared is negative 1, so in the denominator we're really going to get 9 plus 16. In the numerator we have 15 minus 12 because I squared is negative 1. And then we have minus 20i minus 9i, that's minus 29i. Then simplify as much as possible. 15 minus 12 is 3, minus 29i, and then 9 plus 16 is just going to give us 25. And then we could rewrite this as 3 over 25 minus 29 over 25 times I using properties of fractions. Check to make sure our fractions don't reduce, but 3 and 25 are relatively prime, and 29 and 25 are also relatively prime, so they do not reduce. Let's try it again. We have 3 plus 2i divided by 4i. Now for this one, I want to say there's a slightly faster way. If you want to multiply by the complex conjugate, which would be negative 4i, that's true. So complex conjugate of 4i is negative 4i. And that would work perfectly fine. If you multiply by negative 4i over negative 4i, you would get the correct answer. But because we're dividing by a monomial, if you're familiar with rationalizing denominators, then all you really have to do is multiply by that radical in the denominator. And since I is just a radical, the fastest way to do this one, anytime you have a monomial with an I in the denominator, that's a single term instead of a binomial, is not to multiply by the complex conjugate, but instead just to multiply by I divided by I. But once again, if you want to try multiplying by the complex conjugate over the complex conjugate, check yourself. It would be good practice to make sure you get the same answer I do. But now what happens? Distribute the I on top. That's going to be 3i plus 2i squared divided by 4i times I is 4i squared. Well, then that's going to give us negative 2 plus 3i divided by negative 4. At this point, we can simplify. This is then going to be negative 2 divided by negative 4 plus 3 divided by negative 4 times I. I'm just going to clean this up a little bit. Negative 2 divided by negative 4 is positive 1/2. And then plus negative 3/4 is the same thing as minus 3/4 I. And so if you try multiplying by the complex conjugate negative 4 over negative 4i, in the end you should still get 1/2 minus 3/4 I. So now for a practice application problem. The impedance Z in ohms of a circuit element is defined as the ratio of the phasor voltage V in volts across the element to the phasor current I in amperes through the elements. that is Z is equal to V divided by I. If the voltage across the circuit element is 16 plus 2I volts, and the current through the element is 4 minus 2I amps, determine the impedance. So we have a formula, that is Z is the impedance is equal to voltage. Notice that this is our voltage. Notice that this is our current. And so then I can write this as 16 plus 2I divided by 4 minus 2I. Then, if you see you could reduce it, you could do that first, but we could also multiply by the complex conjugate of the denominator. That's going to be 4 plus 2I divided by 4 plus 2I. Then that's going to give us 64 plus 32I plus 8I plus 4I squared divided by, and I'm just going to take the shortcut here. This is really 4 squared plus 2 squared. That's going to be 16 plus 4. Once again, I did really FOIL 4 minus 2I times 4 plus 2I, but because it's a difference of squares, I get the following. Then we're going to get that this is 64 plus 32I plus 8I. That's going to give us 40I. And then minus 4, all divided by 20. That then gives us 64 minus 4 is 60, plus 40I, all divided by 20. Using the properties of fractions, this 60 over 20 plus 40 over 20I. 60 divided by 20 is going to give us 3, plus 40 divided by 20 is 2I. And so this is our answer, and our units is ohms. Now from section 2.3, we do know that the zeros of quadratics are the x-intercepts. And so if we recall the quadratic formula, that is x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Remember that the quadratic formula will always work. Also, you could complete the square, but either is up to you. They're exactly the same. The deal is that something interesting happens here, and that is inside the square root we have this b squared minus 4ac. And if we consider for a moment what happens when b squared minus 4ac turns out to be certain things. And when I say certain things, what I really mean is b squared minus 4ac could be a positive number, could be a negative number, or could be 0. And I claim that this thing called the discriminant will actually identify how many x-intercepts that you're going to have. And so let's take this into consideration. If we find that b squared minus 4ac is equal to 0, well, you get the square root of 0, which is just 0, and so that plus or minus 0 doesn't change any, which really tells us explicitly that there only exists one real solution. Then, if you were to find that the discriminant b squared minus 4ac is greater than 0, that is a positive number, in the quadratic formula we get plus or minus the square root of a positive, which is really going to be plus or minus a number. That is two separate equations, or two real solutions. On the other hand, let's say that b squared minus 4ac is a negative number. That is, it's less than 0. Well, when you take the square root of a negative number, you get a complex number. And complex numbers don't get graphed on our xy coordinate plane the way real numbers do. That doesn't happen. So anytime you have complex solutions, it's actually telling you that there are no x-intercepts. That is, this is a parabola that opens up above the x-axis, and it doesn't touch the x-axis, or it opens down and it's below the x-axis. So the discriminant can automatically tell you how many and what type of solutions you're going to get when you're dealing with a quadratic function. So let's say we want to find the complex zeros, that is all the zeros of the quadratic functions. What are these, and describe what these graphs look like. So first off, if I've got x squared plus 9, if you want, you could use the quadratic formula. But anytime you can, go the easiest route. I see that if I'm trying to find the zeros, that is x squared plus 9 is equal to 0, I can just use the square root property. That is x squared is equal to negative 9. Then when I take the square root of both sides, that's going to leave me with x is equal to, remember, plus or minus, that is plus or minus 3i. What does the graph look like? Well, the parabola doesn't cross the x-axis. And if you were to recognize our transformations, we know this to be true because x squared plus 9 on the outside is actually a vertical shift. And so that x squared plus 9 is the quadratic function that shifts up vertically by 9 points. 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that this is really the parabola that sets right there on 9 and opens up like this, which means we don't have any x-intercept. Now x squared minus 25, on the other hand, if you wanted to take that transformation idea, this really shifts down by 25. I'm going to do a quick sketch. Let's call this negative 25. That is, this parabola will look like this. And it will cross the x-axis at some point. And if we find the zeros, that is x squared minus 25 is equal to 0, add 25, x squared is equal to 25. Take the square root of both sides, plus and minus, x is equal to plus and minus 5. And so specifically, if I look at where this thing crosses the x-axis, I know that it's going to be at the points -5 and 5. Now if I have x squared minus 10x plus 41, let's just find our zeros first. Well, if I want to find my zeros, we could try to factor this one if we so desired, or we could just throw it right into the quadratic formula, or we can complete the square. These are all feasible options, but let's just throw it right into the quadratic formula. That is -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Those will be our x values. And when we do all this arithmetic, we're going to get that this is x is equal to 10 plus or minus the square root of 100 minus 164, all divided by 2, all divided by 2. Then notice that this is 10 plus or minus the square root of -64, all divided by 2. Now, the moment we see the square root of -61, once again, this is going to be some parabola that does not cross the x-axis because the solutions are not real. But if I need to find those zeros, well, let's write them out. That's going to be x is equal to 10 plus or minus 8i, all divided by 2, but then that reduces to be 5 plus or minus 4i. And so those are all of our complex zeros, all of our zeros. And then if we were to consider the graph, I don't actually know all the places that it falls. We could find it. But I do know that it opens up because the leading coefficient is positive, and because it has complex zeros, it does not cross the x-axis. And so it is some parabola above the x-axis. Could be over here, here, here. We would have to figure that out, but it definitely opens above the x-axis. Then if I've got -2x squared plus 16x minus 20, let's use the quadratic formula again. That is, x is equal to -b plus or minus the square root b squared minus 4 times a times c, all over 2 times a. That then is going to give us -16 plus or minus the square root of 256 minus 160 divided by -4. That's going to give us -16 plus or minus the square root of 96, all divided by -4. The square root of 96 will simplify to 4 root 6, all divided by -4. Then notice that I can simplify this even further. That's -16 divided by -4, or +4. And then plus and minus divided by negative is going to be minus and plus. So it's plus and minus. 4 divided by 4 is 1. And so that's square root of 6. And so those are our complex solutions. Now when I say complex, real numbers are also complex numbers. And so this actually does cross the x-axis. Notice that because I have a leading coefficient of a negative, I know that if I were trying to graph this, I would actually get some sort of parabola that crosses the x-axis at two values. Those two values are 4 plus root 6 and 4 minus root 6. It's probably not centered on the x-axis, but I do know that it opens upside down and crosses the x-axis twice. Now we want to find all the zeros of this quadratic function and then describe the graph. So x squared minus 8 plus 25, if we use the quadratic formula, that is x is equal to -b plus or minus the square root b squared minus 4 times a times c, all divided by 2 times a. We then get our x values are +8 plus or minus the square root of 64 minus 100, all divided by 2. That's then going to give us 8 plus or minus the square root of -36, all divided by 2. And that gives us 8 plus or minus 6i, all divided by 2, which will reduce to 4 plus or minus 3i. And so we found all our solutions. And then if we want to know what this function looks like, it's actually going to be a parabola that opens up. I see that there's no negative out front, so it's a parabola that opens up above the x-axis. So the x-axis is going to be below it because we have two complex solutions.